On va commencer tout de suite notre première conférence, CP Violation in Higgs Extended Models, animée par le professeur Per Osland, qui est un physicien norvégien spécialisé en physique théorique des particules. Il est professeur émérite à l'université de Bergen. Professeur Osland a été élu à la Société royale norvégienne de physique de 2010 à 2013. Il est le co-auteur avec Roy J. Grover de l'ouvrage Asymptotic Diffraction Theory and Nuclear Scattering, Cambridge University Press, 2019. Professor Osland, join us on stage.
Bonjour, good morning. I will be speaking in English because my Arabic is not so good and my Berber is non-existent. In Arab I actually know the word shukran, which is more or less the most important word. Okay, so I will move over here to avoid. No, I need to control. Yeah, okay, good, very good. So I will be talking about the Higgs sector or the scalar sector in the standard model. And I have prepared a little introduction here. And let's see if I can make this work. Yeah, okay. I have made two lists here. One with scales going from galaxies at 10 to 20 meters and down to 10 to minus 20 meters. And as you see, we have humans in the middle here, and here are the associated sciences. We have astrophysics up at the level of solar systems, 10 to 10 meters. Biology dealing with humans, then we have chemistry, atomic physics at 10 to minus 10, atomic nuclei, and nuclear physics, particle physics, and this is what I will be discussing. These particles involved here are treated as point-like. They could have a size, but we think of them as being point-like. And now you see the magic of the logarithmic scale. It puts the humans in the middle, which is actually a very fascinating feature of this particular choice of scale, ranging from the largest things we know to the smallest things we know. And by this particular choice of scale, the humans come out in the middle. Sorry? It's okay, it's okay. A little more detail on small objects. We have the atoms at 10 to minus 10 meters. We have the atomic nucleus around 10 to minus 12 meters, proton 10 to minus 15. And for the quark, as I said, we think of them as point-like, but there's an upper limit of about 10 to minus 18 meters. We can make a comparison of forces and particles. On the left, I have listed the forces which were known in the 90s. We have electromagnetism, we have the weak nuclear force, we have the strong interactions and gravity. And we think of these as being transmitted via force particles For the electromagnetism, we have the photon. For the weak interactions, we have, since the 1980s, we have the W and the Z bosons explaining those. And for the strong interactions, we have the gluons. They hold the nuclear matter and the proton together. And then we have this is a hypothetical particle, the graviton, transmitting or enabling gravity. And these forces act on two categories of particles, the leptons and the quarks. Here is the well-known electron, and there are antiparticles, the muon and the tau. These are similar to the electron but heavier, and they have associated neutrinos which are chargeless, they have no electric charge. And then we have the quarks which build up the proton, the neutron, the pions, etc. 6 of them, U and D, are the lightest ones. C and S come next, charm and strangeness, and then top and bottom. This was the situation at the end of last century, and the big mystery was how can the W be massive without spoiling the theory? A possible mechanism had been suggested in the 1960s by Peter Higgs and also others, but that theory had more or less been dormant then for 20 years. That mechanism predicted the existence of a new scalar which was discovered at CERN in 2012. That was the famous Higgs particle. So in a sense, the standard model now refers to all we know about particle physics. That was complete because no one had an explanation why the W was massive and everything else was fine. This is a picture taken from the EPS conference in Stockholm in 2013. This is Peter Higgs. He is explaining the history of having his paper published. It was first rejected by a referee who found something he didn't quite like or understand. And then it was modified a little bit and accepted for publication in the Physical Review Letters. And in this refereeing process, he was made aware by the referee, who he later learned was Nambu, who also got the Nobel Prize. He learned that there was another paper dealing with similar issues by Angler and Brodt. These are two Belgians involved in this work. And here is a picture from my camera lying here in the front, taken in Stockholm in 2013, Peter Higgs with Angler, and this you may recognize as Fabiola Gianotti, now Director General at CERN. She, of course, played an important role in making the experiments possible. So a quick reminder of the standard model. We have a potential. Phi is here. Is the microphone working okay for those in the back? Phi is the field of the scalar Higgs. We have a potential which has a quadratic term and a quartic term. And minimizing the potential, one gets a relation between the mu squared, this coefficient, and the lambda here. And there's a kinetic term which is quadratic in derivatives of the field. But this is no ordinary derivative, it's a so-called covariant derivative, which in addition to partial differentiation contains two terms involving vector fields. That's what makes it a covariant derivative. And sigma here is the Pauli matrix, 2 by 2. And this phi is a so-called spinor, which is a two-component quantity. Each of these is a field which is something which can create the particle from the vacuum or remove a particle from a state containing particles. It has an upper component which carries electric charge, indicated by the plus, and the Hermitian conjugated of this, the 5 dagger, which will come here, that has the negatively charged field. And in the lower component, there's the electrically neutral part, which is here written out as a constant plus a real and an imaginary part. And the important feature of this potential is that it can have, for suitable choice of these coefficients, it can have a vacuum value when phi plus and eta and chi are 0. It can still have a non-zero value, which is represented by this V. And this V then, because of the covariant derivative structure, comes together with the W field, and that is how one generates a mass for W in the standard model. It's given by the strength of this interaction, the G appearing in this covariant derivative, and the V, the vacuum expectation value of the field, and that's a factor of 2. So a couple of comments. The vacuum expectation value when the charged field is 0 and these fields in the lower component are also 0, then we have only the V. And without loss of generality, one may choose this V to be real by just performing a phase rotation on this capital phi. I mention this because when we go to 2 and 3 doublets, then phases will play a role, but here it can be removed by just phase rotation. So the existence of massive gauge bosons W and Z was explained by this Higgs mechanism, that a Higgs particle had been discovered, but there are still problems, and 2 of the more important ones are listed here. One is that more CP violation is required to generate the asymmetry between baryons and antivariants, or between matter and antimatter. And we know the universe is mostly matter, very little antimatter. That's one issue. The other one is that it does not explain dark matter. It is known from various experiments that there is a lot of matter in the universe which is invisible. It does not interact with photons. And either of these 2 problems can be solved by adding another doublet, but not both of them. So I'll then switch over to 2 doublets. In 1973, T.D. Lee, an American physicist of Chinese origin, he pointed out that if one had 2 doublets, then time reversal symmetry, or equivalently so-called CP, C is charge, P is parity, could be violated spontaneously, even if it was not introduced in the theory from the beginning. And this is a possibility if one of these gets a complex vacuum expectation value. So the quantity referred to as V in the standard model, here there will be a V1 and a V2, and they have to have different complex phases. One of them has to be complex with respect to the other. Now the most general potential has this structure. There are 3 quadratic or bilinear terms, and then there are these 7 quartic terms. This model, instead of the standard model, which has only 1 Higgs particle, this has 3 neutral states, and it has a pair of charged ones, and I have listed them here as H1, H2, H3. and usually H1 is taken to be the one that is discovered at CERN. So there are many parameters. As I said, the quadratic terms, these two have to be real because the whole thing has to be Hermitian or real. But this one can be complex because we add the Hermitian conjugated part. So there's a total of 4 parameters here. And then we have the quartic ones. 4 of them are real and 3 are complex. In total we have 14 parameters. Now, these fields may be transformed without changing physics. One can rotate them by this U, which is a 2 by 2 unitary matrix. As long as this is unitary, the physics will not change, but the coefficients in the potential will change. And in particular, when we choose such a rotation to remove this n12 squared term, in addition, one may choose a phase rotation on one of them with respect to the other to make lambda 5 real. So in the end, there are only 11 independent physical parameters. Now, masses and couplings among the scalars are given by the vacuum expectation values and the parameters of the potential. But the inversion is not unique, since 11 is less than 14. And it's therefore convenient to introduce what we call the physical parameter set, which has 4 masses. This is the charged scalar mass. There are 3 neutral ones which have their masses, and then there are some couplings. These are 7 couplings, and I will define them on the next slide here. We start with the kinetic term in the Lagrangian. It has 2 contributions to the phi 1 and phi 2, the 2 doublets. And it will contain mixing between the scalar fields and the gauge bosons Z and W. And we can extract from the kinetic Lagrangian a term involving Z linearly and 2 neutral Higgs fields, one of which is acted on by a derivative that will contain this EK and these E's, they represent the coupling between, in this case, between 2 scalars and 1 Z, or between 2 Z's and 1 scalar, or between 2 W's and 1 scalar, and this is a derivative coupling analogous to that one. These can be expressed in terms of the E's, and don't worry about the F's. These E's satisfy a relationship that the sum of the squares is given by this vacuum expectation value, B squared, which is the one that determines the mass of the W and the Z. So these are the 2 important ones in that correction of terms. And furthermore, among the 7 couplings, we have 3 Q's. Those represent the couplings between the neutral Higgses and a pair of charged ones, H plus H minus. We refer to that coupling as QI. And then there's a quartic coupling needed. We have taken the one between 2 charged plus and 2 charged minus scalars. Now, a word about symmetries. In addition to this 2 by 2 unitary rotation that I mentioned, we may also consider a complex conjugation, and the complex conjugation may be just a straight complex conjugation, or we may introduce a matrix here to twist it, to let phi 1 go into complex conjugated of phi 2, or some linear combination of 1 and allowing also such transformations, we get a total of 6 different symmetries, which are listed here. SO3 is the highest degree of symmetry, and CP or CP1 is the lowest degree of symmetry. But these are not automatically satisfied in contrast to what we get when we apply only this view. If we want these symmetries, we will have to restrict the potential and the waves. Here is an example, CP transformation. Phi goes into phi complex conjugated. And if the potential is not invariant, then we say CP is explicitly violated. But even if that is not the case, it could happen that V1 and V2 is not invariant, and then CP would be spontaneously violated. And that's the possibility that T.D. Lee pointed out in '73, that even if we have a real potential where CP is not explicitly violated, one web may be complex with respect to the other, and then CP would be violated spontaneously. And as I mentioned, this is interesting because it could contribute towards explaining the excess of matter in the universe. Second example, Z2 transformation, then one of the fields would flip its sign. In this case, phi2 would go into minus phi2. Again, if the potential is not invariant, then Z2 is explicitly violated, but if the vacuum expectation values are not invariant, then Z2 would be spontaneously violated. But in this example, with phi2 flipping sign, if we had the vacuum expectation value of phi2, if that was 0, this would not matter. So Z2 would then be respected by the vacuum if it happened to be 0 for one of the webs. And this is known as the Inert doublet model. It has one doublet which contains a candidate for dark matter. And that candidate for dark matter would be the lightest neutral state. The doublet would have a pair of charged ones and 2 neutral ones, and the lightest of the neutral ones would be a good dark matter candidate. Because it does not couple to gate bosons and not to fermions. It's stable. So, as I said, these conditions for having certain symmetries can be expressed in terms of the physical quantities. One doesn't need to go to the potential parameters, which form an over a numerous set of quantities. It can be decided straight from the physical quantities. And CP violation, here are 2 cases identified. One is referred to as case C. EK and QK are 0, meaning that one state, K is 1, 2, or 3. One of them decouples from gauge bosons and from the charged pair. And then there's a case D, in which case there is a connection between the charged Higgs mass and the masses and couplings of the neutral ones. In addition, this quartic coupling Q is also related to the masses of the neutral ones and the couplings E and Q, which refer to couplings to the gauge bosons and to the charged scales. And this case allows spontaneous CP violation. In the second example, Z2, then there are 2 cases. One of them is referred to as CC. Then 2 of these neutral states would have to decouple
from the gauge bosons and from the charged pair, and that corresponds to the IDM, the one that could have a dark matter candidate. And then we have the second case, CD, which is more complicated. It has one of them decoupling from gauge bosons and the charged scales. That condition supplemented by a constraint on the charged Higgs mass and this quartic coupling Q. And in both of these cases, CP will be preserved. So in summary, on the two Higgs doublet model, which is actually very much worked on and studied, we can have additional CP violation in the scalar sector, or we can have a dark matter candidate, but not both. So, and both of these are refuted by experiments. So then, not reaching our goal with just two doublets, let's have a look at the possibility of having a third one. And just to remind you, in the case of the discovery in 2012, that required only one doublet, but it did not address then the issues of CP violation and dark matter. Now, the most general potential with three doublets has 46 parameters. And of course, if you introduce so many parameters, you don't have much predictivity anymore. You can fit anything. So in order to retain some predictivity, we can reduce the number of parameters by imposing a symmetry. And here we have introduced a so-called S3 symmetry, which is a permutation among three objects: 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, and so on. And this symmetry is imposed on the three fields, phi 1, phi 2, phi 3. The corresponding symmetry was written out in 1979 by a certain Berman who was working in New York at the time. It has bilinear terms and quartic terms. The bilinear ones are referred to as B2 and the quartic ones B4. So it has a total of 10 parameters if they are all taken to be real, meaning there's no explicit CP violation. And some people have argued that one should use so-called irreducible representations for these three scalar fields. And you see that the sum 1, 2, 3 is an invariant under S3. Any permutation of two of them leaves it in the same form. So that singlet can then be supplemented by a doublet, H1 and H2, which can be written in this form involving phi 1 and phi 2 and phi 3. And in this terminology, this notation, the potential was written out in 2014 by two Indians, Das and Bay, and it has this form. There's a quadratic term, B2, and the quartic one, which has 8 coefficients referred to as lambdas. So this potential has no symmetry under interchange of H1 and H2, but it is symmetric if I flip the sign of H1. And that corresponds to this Z2 symmetry we discussed for the two Higgs doublet model. There's a special case when one of the quartic terms vanishes, lambda 4 being 0, then one has an SO2 symmetry of the potential, but in that case, because of that symmetry, there will be massless states, and massless states are unwanted because they are excluded by experiments. This potential was studied in some detail in 2016, and we identified 11 real vacua and 16 complex ones. And more recently, we have studied 2 of these vacua, looking for implementations of dark matter and CP violation. These are labeled R21A. That is the R stands for real, and the C here is complex, and the Roman letters 2 and 3 refer to how many conditions we have. There are conditions coming from the minimization of the potential, setting the derivative to 0. This has the shape of the first one, I should call it phi 1, it's H1. It's the one of the doublets which has vanishing vacuum expectation value, and then the other doublet has a non-zero vacuum expectation value, and the singlet has a non-zero one. And there's a corresponding vacuum where this V2 is complex. It has a complex phase. So that smells of CP violation, but just having a complex phase is not necessarily enough to have CP violation, but in this case it leads to CP violation. And in these models, the inert doublet, the one that contains the dark matter candidate, is associated with H1, the field having a vanishing vacuum expectation value. And the fermions, which are coupled to the Higgs field via so-called Yukawa couplings, they are taken to be singlets under S3, so they couple to HS, which is in this position. So this R21A model, it has 3 SU2 doublets. H1 and H2 are in a S3 doublet. One is inert, has a vanishing vacuum expectation value. It contains physical states, a charged one and 2 neutral ones of opposite parity. H2 is active in the sense that it has couplings to gate bosons and to well, it's a complicated story, but it is involved in interactions with other particles. And HS is the S3 singlet that's also active, and that coupled to fermions because it has non-vanishing vacuum excitation. In the C3A model, H1 is again the inert one, but now H2 and HS will mix. These are the active members of the S3 doublet and singlet. They mix. Physical states, a charged one, 3 neutral ones, and CP is now violated because of this mixing. Again, HS, the singlet will be responsible for these couplings to fermions. So here's what we found in the case of R21A. The IDM model, which has been very much studied, is based on the Z2 symmetry. It allows for masses in the range from maybe 60 to 80 or 70 GeV. This is the mass range of the dark matter. And then in addition, it allows for heavy dark matter around 500 GeV. This has been extended to allow for a third doublet in a model referred to as IDM2. Again, there's a range of light values, mass values allowed, and heavy ones, about 500 GeV. And here are a couple of other models with 3 doublets worked on by co-hosts and collaborators. They again have light solutions and heavy ones. And this R21A, which we worked on, does not allow for the heavy ones. It is restricted to the low masses from little more than 50 to something like 80 GeV. And the C3A model, which we worked on more recently, does not even allow this region here, and not the heavy ones, but it allows for very light dark matter from about 6 GeV and up to 45 or 46 or something. So an important observation here is that in contrast to these other models, the S3 based ones do not allow for the heavy dark matter candidate, around 500 GeV. To obtain these possible ranges of masses, we had to do parameter scans over the parameters of the model, and we did that in 3 sequential cuts, imposing theoretical and experimental constraints. The theoretical ones are to impose perturbativity, stability, and unitarity, and the LEP constraints. LEP was another experiment, well, it was actually the name of an accelerator complex at CERN. They obtained some constraints on the non-existence of light-charged particles. In cut 2, we require that the coupling of the standard model candidate to gauge bosons W and Z should be in agreement with experiments. This has been measured precisely at CERN. Likewise for the Yukawa sector, which describes the couplings to fermions. And then there are electroweak position observables and beat physics constraints. I will comment a little bit on this. And cut 3, we look at the standard model candidate, its decay to invisible stuff or to gammas should be in agreement with experiments. The dark matter relic density should be in agreement with experiments, and we should respect the non-observation in dark searches. So a technical note here on some constraints. The lightest neutral state, H1, should have the mass in agreement with experiments. Couplings to gauge bosons and fermions should agree with measurements to within 3 sigma. Sigma is the uncertainty in the measurement. And there should be no charge state below 70 GeV. This is one of the LEP constraints. And the coefficients in the potential, these lambdas, should not be too large. This has to do with perturbativity and unitarity. So in the case of R21A, I show here some plots of allowed values. Light blue is with unitarity is somewhat relaxed, and dark is with a more strong constraint on unitarity. And these planes are mass planes of allowed values. In this case, we have to distinguish between which of the 2 neutral ones is lighter. Here it's eta, which is lighter than chi. And the masses range up to 600 GeV for the lightest charged one, and something similar for the heavier charged ones. And here in the left, I show the 2 members of the Inert doublet, their allowed mass ranges, and here the allowed mass ranges of the active neutral states. Then we have the B constraints. The B quark can transform itself into an S quark with the emission of a photon, and this takes place in the standard model via this kind of diagram. The B quark emits a W, which then recombines with the quark to make an S, because these couplings are non-diagonal in flavor. And from the intermediate line, a photon is emitted. But if we have charged scalars in the model, then the photon could also couple to the charged scalar, and this leads to an additional contribution. And this is at the quark level. At the meson level, it's a B meson, which goes into any meson containing an S quark and a photon. The rate for that is quite well measured, and in order not to be in conflict with these experiments, the charged Higgs contribution here requires the mass of the charged one to be heavy. It cannot be too light. So this is one of the constraints imposed on these models. And then we have the dark matter relic density, referred to often as capital omega H squared. As you remember, about a quarter of all the matter in the universe is dark, and the evidence is based on many different observations. Here's a list given by Catherine Fries in 2008. The traditional one is the rotation curves of galaxies, which showed that the more matter was present than what we see, and this evidence has been supported also by weak lensing measurements, hot gas in clusters, primordial nucleosynthesis, and the microwave background experiments. The early universe physics plays an important role here. The Big Bang was 13.8 times 10 to the 9 years ago. At that time, according to the theory, there was an equilibrium, a thermal equilibrium between all particle species. AA bar could go into BB bar, could go into CC bar, etc. But while this happened, things expanded, and so the density got lower, and the heavier particles froze out. They were no longer able to maintain equilibrium, and if they were stable, they would still be around today, and this is the dominant theory for dark matter, that it is left over from the early expansion of the universe when particles could no longer maintain thermal equilibrium. So given a particular model, including masses and couplings, one can calculate this quantity today and compare with experiments. And for this purpose, we use a software called Micromegas, which is developed by the Moscow ANSI group. And in the early universe, there were losses of dark matter. They could annihilate to a W pair, and also they could get lost due to this so-called portal coupling, in which two dark matter particles come together and form a Higgs particle of some kind, or two of them. And in the IDM, which had this possibility of heavy dark matter, these couplings are tunable, so one can tune them to a desired value to get agreement with experiment. But in the case we have studied more recently, these S3-based models, this so-called portal coupling is not an independent parameter. The coupling actually grows with dark matter mass. And I have some plots here showing this coupling, how it grows. And this is the region 500 GeV, also where we don't find solutions, and it's because this portal coupling between two dark matter candidates and the Higgs boson gets too big. So, in fact, this is the result of our scan for the R21A. The experiment says this quantity should be around 0.1. And in the low mass region, this is the mass of the dark matter candidate. In the low mass region, that's possible. But beyond 120 GeV, it's no longer possible. And here is the similar plot for C3A. Again, you see at high masses, one cannot get enough dark matter in these nodes. Then there is a constraint from direct detection. There are dedicated detectors. One of them is the Xenon 1 ton in Gran Sasso, Italy. They are waiting for something to happen, and what they are looking for is that the dark matter could scatter from a xenon atom to give, in the final state, the invisible dark matter, but the xenon could recoil, and that would be a signal they could detect. This kind of experiment, they take place in these caves deep underground to suppress background from cosmic rays. One example of which could be muons from neutrinos. And they also searched for at CERN, but there's an important background, which is that many of the experiments at CERN produce neutrinos in the final state. So for the R21A, I have some plots here of the final constraints on the masses. Cut 1, 2, and 3 in different colors. The final cut is the gray one. So the charged ones, this is the lightest charged particle, and the heavier one, they populate this region around 2 to 400 GeV, and here is the dark matter candidate around 50, 60 GeV, and the accompanying one up to 400, and these are the heavier companion of the discovered Higgs boson. Similar plot for the outer model, we have looked at C3A. The scale is here different. This scale goes only up to 400 GeV. And for the dark matter candidate, you see it's very low masses. So I have come to my conclusions in more or less on time, I guess. I would conclude that symmetries play a crucial role in multi-Higgs models. These multi-Higgs models provide interesting scenarios for dark matter. I'm not saying that we have really explained dark matter, but we have candidates, which is one possible solution. Symmetries are needed to stabilize dark matter. In these three doublet models, it's the H1 to minus H1 symmetry, which is a remnant of the S3 symmetry. It's that symmetry which provides stability. So the R21A model that in this way provides dark matter without imposing an ad hoc symmetry for stability. And the C3A model, I didn't elaborate on that, but in addition to having a dark matter candidate, it also provides CP violation. So multi-Higgs models have a rich phenomenology. And an important feature of these particular models is that the accompanying particles, which one should be looking for at CERN, they are relatively light. Relatively light means that they should be accessible by current experiments. So we are eagerly waiting for results from the LHC. And that was actually my last slide, so thank you very much. I will be happy to try to answer any questions if there are some.
Hi, thank you for everything. I just want to know, is there any relation between the cosmic inflation and the multiverse?
I did not understand the question. Can you repeat it, please?
Can you repeat the question, please?
Is there a relation between the cosmic inflation and the multiverse theory?
You refer to inflation, but what aspect of inflation did you refer to?
After the Big Bang, shortly after the Big Bang, it was
right.
I think
inflation, yeah.
Yeah, and some physicists found a cold spot, and I read in an article that this cold spot may refer to that it was two Big Bangs, and after they create two universes, it was something like that. I didn't really understand.
I think I don't hear all the words, but you seem to refer to a cold spot in the early universe related to the Big Bang. And I am afraid I have nothing to add to that. I don't know the story.
Okay.
Sorry.
Okay. Another question, please. Is it possible to create a wormhole?
Again, I'm not an expert on wormholes. I know that some theorists would claim they exist, and you may try the question on Susskind tomorrow. He may have something to say about that.
Thank you.
I have a question about a particle, or I don't completely understand it. Could you possibly explain what is a boson exactly? Because I don't get to really understand the concept.
You mentioned a boson. What was the question about the boson?
I think it's a kind of particle or something related to mass.
Well, we distinguish two categories of particles, the bosons and fermions. The fermions have half-integer spin, and the prime example of that is the electron. And the bosons have integer spin, and one example of that is the photon. Photon has spin 1, which is an integer. And these particles I talked about, they are scalars, meaning they have spin 0, which is also an integer. And I did not say much about the fermions, which are quarks and leptons.
Because this is a question that I had before watching your intervention. Okay. So thank you.
But let me add that there are some people who have discovered that if you
go out of 3 dimensions down to 2 dimensions, you can have intermediate situations between fermions and bosons, and those are called anyons. But that is not present in 3 dimensions, so we have to choose between fermions and bosons.
Thank you. Thank you so much.
First, I just want to ask you about the presentation, and I have only one question about where did the particles gain their masses from the model standard model? Where they gain their masses?
Could you try to repeat without the mask? I didn't hear very well.
My question is, from the standard model, where the particles gain their masses, the mass of particles?
Okay, that is a fairly easy question. There are in the standard model there are massless particles like the photon and the gluons. They are massless, and then there are the heavy gate bosons of the electroweak theory, W and Z. They get their mass from the vacuum expectation value of the Higgs field, which is coupled to these gate bosons W and Z via this covariant derivative. And then we have the fermions, the electrons and the quarks, and the mu1 and the tau. They get their masses also via the vacuum expectation value. There's something called Yukawa coupling, in which there are 2 fermion fields and 1 scalar field. And when the scalar field gets the vacuum expectation value, that amounts to a mass term in the mathematics describing those fermions.
Okay, just following that, I have another question. Is that proved experimentally, or is just an explanation or a theoretical explanation?
This is a theoretical explanation. One cannot, as far as I know, one cannot measure the origin of the masses. I don't know any way to do that. But according to this theory, the interactions of those fermions to the Higgs field will have to be proportional to the mass, since it's the same coupling giving the mass and the interaction. And that has indeed been tested for some of the particles, so that agrees. But of course it has not been tested for all particles. Some have too low masses, they couple too weakly for this measurement to be possible.
Okay, thank you so much.
I just want to ask if theories with 4 Higgs doublets were studied before, and if no, do you think they will make a better candidates to explain that manner?
Sorry, again I didn't hear very well.
Theories with 4 Higgs doublets.
Oh, 4.
Do you think they were studied before or not yet?
The problem when you introduce more fields is that you feel an obligation to do the general theory unless you have a good argument to restrict it to some smaller number. And when you introduce 4 doublets, you get very many coefficients, very many unknown in your equations. And you don't have that much productivity. So I think for a while people will there are papers on 4 doublets, but not many.
Okay, thank you.
I want to ask you, sir, about can you explain the difference between behavior of a strong nuclear force and electromagnetic force? For example, for a hydrogen atom, we have an electron plus a proton. If we calculate the mass of electron and add it to the mass of proton, we find this a little small, bigger than the mass of atom itself. But in the proton, we find that the mass of quarks too small than the mass of the proton itself. So it seems like the the behavior of the nuclear strong force, different than the behavior of the electromagnetic force.
This question could be answered in different ways. If you think of the mathematics of these two interactions, the main difference between electromagnetism and the strong force is that the strong force has a bigger coupling. The QCD coupling is bigger numerically compared to the electromagnetic coupling given by the fine structure constant. But in addition to that, there is the issue of asymptotic freedom and the fact that the strong force, when you pull two charges apart, it becomes non-perturbative, so you cannot describe it with the ordinary mathematics. But maybe your question was more related to the fact that the proton mass is big compared to the masses of the quarks from which it is constructed, and that has to do with what is it called, confinement, which is an unsolved problem. But you know from other systems that when you have system in a potential, the total energy may be quite different from the energy of the ingredients. It is not an additive thing.
Thank you.
My question is about the tree HDN. I want to ask that you pointed out that the Higgs could decay into a dark matter. Is there any experiment that working currently to detect any deviation of the prediction of the standard model from this model?
Sorry, which particle could decay into dark matter?
The Higgs, each one.
Yeah.
In
Okay.
cut tree.
Yeah. Yes, there are constraints on this. These are referred to as the invisible width of the Higgs. This is a feature of these models which I have discussed, that the Higgs couples to dark matter. That was this portal coupling I referred to in the early universe. It can also go the other way, that the Higgs could decay into dark matter if there is a coupling non-zero. But the problem experimentally is that dark matter is invisible. You don't easily detect it. One kind of experiment is if it's produced together with something else, then you can detect that something else, and you see there's a missing transverse momentum. There's a mismatch in the momentum conservation.
Yes. So the Higgs, we have, according to the standard model, we have some decay rate. So we could differentiate between these two models. We found the difference experimentally, and this could be a proof of the dark matter without detection of the dark matter.
In the standard model, there is no coupling to dark matter because dark matter is not part of the standard model. In these models I discussed, there is a coupling which is written out in terms of some quantities, and when you can constrain those quantities, you can determine that coupling, and you know then how much the Higgs should decay to dark matter.
No, the Higgs, we calculate the weight of the Higgs decaying into two photons.
Right.
And according to 3HDN, this could, so the Higgs will decay into two photons and also to dark matter.
Right.
So we find a difference between experiment and the theoretical calculation from the standard model.
Well, when you say in the 2HDM Higgs,
3HDM.
2HDM.
3.
Sorry?
3HDM. 3.
Oh, 3. Yeah. Okay.
You got 3.
Yes, but you're asking about experimental evidence in this direction. You can only establish upper bounds. You know that for the observed Higgs, there's only one observed so far at 125 GeV. There are upper bounds on its decay to invisible stuff, but there's no measurement. And also all models which pretend to describe nature, they have to pick coefficients, couplings, such that you reproduce the decay width to two photons that has been observed. So at the moment there's no discrepancy, no way to distinguish these experimentally.
But doesn't mean the model is wrong. Do not exclude the 3HDM. Not yet.
No.
Another question about the Higgs mechanism in the standard model. That in order to have the value of the Higgs field different than 0, we assume that mu square is less than 0. Somehow it's like a scalar field with a negative mass.
Well, that is just a matter of terminology. If instead of calling it mu squared, you'll call it x, and then you can let x be negative, I don't think that's the problem.
No, in order to have a value different than 0,
Yeah.
we assume that mu squared is negative.
Right.
And mu squared is the mass of the scalar with the Higgs field.
No, it's not the mass. It's not the mass. It's just a parameter of the potential. It's a parameter in the potential. It's not the mass.
Because in other theories, for example, when we take the Lagrangian of the fermionic field, we write m times psi bar times t. And also for a scalar field, we write the mass term times psi adjoint times t.
Yeah, okay. It has the mathematical structure of a mass term, but because of the additional lambda phi to the fourth term, it does not end up playing the role of a mass, even if it has that form mathematically. It's a combination of mu squared and lambda, which becomes the real mass squared.
Thank you, sir.
And that's because the minimum of the potential is away from the origin. At the origin you have this mu squared, but then the potential goes down, and it's the coefficient controlling that oscillation out there which shifts the mass.
Thank you, sir. It's clear.
I want to ask a different question. As a physicist and from your life experiment, what can you recommend to all young students who want to get into physics, and especially theoretical physics?
Well, I'm tempted to quote a colleague of mine in Norway who said, it doesn't matter what problem you give the students as long as it's difficult. So that would be my advice to you. It doesn't really matter what you do as long as it's sufficiently difficult, meaning it's challenging. You need to think to solve it.
Thank you very much, Professor, for sharing with us your knowledge. Thank you.